Testing. Yeah. Thanks a lot, Steve. Thanks, Steve. And you couldn't have set me up better for my talk because we use a lot of that stuff. All right, I'm Ian. I'm very humbled to be here in the midst of a lot of AI and HPC brain power. I'm a humble engineer. You know, I use the stuff that you guys create to do engineering analysis. And what I want to talk to you today is about the future of engineering and how we're using Cloud HPC and Cloud AI to do really cool engineering stuff. And it's going to be a game changer for engineers. So, engineers have been making science fiction reality for 10,000 years. We designed the pyramids, we designed aqueducts, we designed the Appian Way, we designed airplanes, and everything around you was designed by an engineer. I'm an aerospace engineer myself, so I kind of think about things in terms of the history of aviation. And if you take a look back at the 1940s and what engineers were able to do with the tools at their disposal, they had draftsman tables, they had computers, but a computer back then was an actual job. It was a job title. There were computers that would sit down and solve large sets of partial differential equations on massive spreadsheets. And they were able to design some really cool stuff. Like they designed, does anybody know what this plane is? P-51? P-51D. Wow, he even knows the letter, the version of the P-51 that this is. So yeah, it's a P-51D. I didn't even know that. But they were able to design this, I think in like 60 days or something like that. Crazy amount of speed to design that aircraft because, you know, we were getting bombed by the Germans and we needed a P-51. All right, fast forward a little bit to when the actual, like what we think of a computer came around, which was like a terminal and a mainframe in the 60s and 70s. What did engineers do with that? Well, they designed cooler planes. Does anybody know what that plane is? You can't answer. Does anybody know what this? F4, right, yeah. Really cool jet air superiority vehicle in the Vietnam War. Pretty fast, awesome stuff. Didn't have a machine gun, which was one of its biggest deficiencies. Fast forward again, and we got personal computers in the 80s and 90s, and engineers designed even cooler jets. So what's this one? F-22, Raptor, yeah, really cool stuff. Now, we're at the dawn of a new age of cloud computing, Cloud HPC, Cloud AI. What do you think engineers are going to do with that kind of power? We're going to be flying around in Iron Man suits, and we'll be thinking, you know, hey, back in the day, these tokamaks were like the size of gymnasiums, and now we can squeeze them into a suit, and we can have fusion-powered rocket suits, maybe. So let's talk about computer-aided engineering. Who in here is a mechanical engineer or electrical engineer by training or academics? Okay, cool, we'll get a couple of people. When engineers have an idea, today we sit down, we draw that idea up on a computer, we try to simulate it, we do, you know, those first-order physics, first principles physics, as Steve mentioned, and then we analyze the results. And during all 20 years of my career doing this, I've been doing it on a laptop or, you know, desktop. If I was lucky, I had a 36-core, what I would call a high-performance computer. But most engineers do this today on desktops and laptops, and we do this over and over and over again, endlessly. And the interesting thing is that there's 100 billion core hours of compute power that's consumed by these engineers worldwide. All of it's happening on-premise, in labs, on laptops and desktops and stuff. It's a problem. The solution is what we're building at OnScale. I don't want to get too salesy here, but what we do is we strip out the multiphysics solvers, you know, those really compute-intensive portions of CAE. We put them up on the cloud, and we actually build this, you know, scalable, elastic Cloud HPC infrastructure where an engineer can send a problem up, or a set of problems, could be a million simulations, or one massive billion degree of freedom simulation, and then we get them the results back in the fastest way possible, and we abstract all the cloud and the AI and sort of the IT infrastructure away from the engineer, so the engineer doesn't know exactly how their results are coming back or how they're being calculated. They just want the data. And we do that hundreds of times faster. In some cases, it's tens of thousands of times faster. The only reason why I didn't put tens of thousands of times faster here is because you probably wouldn't have believed me, but it's true. We were founded in 2017 by world-class engineers and scientists. We're venture-backed. We're growing quickly. And the future of engineering, from our perspective, is the combination of a couple things. One is workflow. You got to have nice, easy ways to interact with this other stuff. You got to have world-class multiphysics solvers. Those first-order physics or first-principle physics solvers that are very computationally intensive. You got to have some AI in there because you're not always going to be running those first-order physics problems. You want to use AI to train models to get more efficient. And then, of course, you want Cloud HPC. Every engineer wants a supercomputer in the cloud to run their toughest models. I've never heard an engineer say that they had enough computing power, enough RAM, enough cores to solve their problems. So that's what we're building. The applications that we're going after are initially high-tech applications. So think about like biomedical devices, sensors for driverless cars, IoT sensors. These are all markets that are super competitive. They require massive amounts of computational workloads. They're bursty workloads. So like in Q1, you may be getting ready to start a project. In Q2, you need a ton of computational horsepower. And then in Q3, you're just analyzing results. So you don't need all of that, all those computers. So that's a nice thing about the cloud is we can handle that bursting nature of these workloads. And we're solving multi-billion-dollar pains. So I also sort of became a MEMS engineer too. So this is sort of a MEMS sensor design flow. And the traditional cycle is you got 6 months to launch a product. All right, you do a little bit of computer-aided engineering up front, a couple of simulations to give you some idea of how your device is going to work, and then you freeze the design and you go make the sensor or make whatever it is you're designing. You manufacture it, you make prototypes. Then you got to take those prototypes and put it into a system. You got to verify the full system, and then after 6 months, you get to this point where like, hey, did that work? Does my sensor work inside of this smartphone, for example? And if the answer is no, you go back and reiterate. And you spend another 6 months and another $1 million. So the problem is the CAE bottleneck. People want to have lots of computer-aided engineering horsepower, but they're limited because they're using on-premise computers, old school legacy physics solvers. They're not using AI. And they're only able to look at like very, very small design spaces, 10 different designs, let's say. And what that translates into is like, as you're going through this project, your cost is increasing, but your risk really isn't decreasing. Engineers should be doing a lot more upfront analysis to reduce that risk curve. So let's imagine a world in the very near future where we're going to take that CAE funnel and we're going to make it massive, as big as the funnel needs to be. And we're going to do like millions of simulations instead of 10 simulations. That's going to break that bottleneck. We can also look at more advanced simulations. So we can do not only our device simulation, but we can put that device into something like a smartphone and see how it works on the smartphone and do system level optimization. We get a ton of data out of that. So what that does is when we freeze our design, it reduces our prototyping, manufacturing time, and it also reduces our system verification time because we've given a bunch of data to algorithm engineers from the simulation, and those algorithm engineers can start writing awesome algorithms to make the sensors work inside of a phone. So what we've done is we've reduced risk, we've reduced cost, and we've reduced time. Now imagine doing that for every engineering discipline, not just sensors, but flying cars, Iron Man suits, whatever. So let's talk about a real-world example. We have some customers that are in the RF group. Everybody wants a 5G phone. Who in here has a 5G phone today? No one's got a 5G phone. How long have you guys been hearing about 5G? You've been hearing about 5G for Oh, he works travel? He's got the first 5G phone, awesome. The real hang-up with 5G is the new spectrum that these RF devices have to operate. 4G was up to 2.4 gigahertz, 5G is up to 6 gigahertz, and then millimeter wave, 26 gigahertz and above. So it's really, really complicated. No one's done it yet. If you go talk to an honest engineer in one of these RF companies like Broadcom or Skyworks or something, they'll tell you they have no idea how they're going to solve this problem. They just know that it is a problem. What we're helping them do is actually do massive billion degree of freedom simulations of an entire RF front end. So, antennas, filters, switches, all of that stuff that they couldn't do before. And we're helping them optimize these 5G front ends to make your next 5G smartphone a reality. This is impossible to do with on-premise computer-aided engineering. They have to do this in the cloud. There's not enough compute power on their local data centers to do these types of simulations. Let's take another use case, fingerprint sensors. So most people have a fingerprint sensor in their phone. Apple and Samsung have been trying to put ultrasonic fingerprint sensors into phones. And ultrasound is cool because it can go through things like the display. So you can have like a fingerprint sensor under the display, and you don't have a button there, and it just senses through the display. And they do that with what is called a MEMS device. This is kind of where I cut my teeth as an engineer and entrepreneur. And these MEMS devices are really complicated. Imagine taking an ultrasound thing, like you guys have all seen ultrasound at the doctor's office to look at babies in the wombs and organs and stuff. Shrink that down, put thousands of them onto a little piece of silicon, and then stick that into a phone and use it as a fingerprint imaging system. It's pretty complicated. It's tough to do. What we've allowed them to do is, again, do this all in 3D, massive billion degrees of freedom simulations, and then get a bunch of data. So when Steve was talking about using simulated data to train AI algorithms, that's our jam. That's what we do. We generate all the fingerprint sensing algorithms simulated, and then they can train their AI to make this fingerprint work. Whereas 5 years ago, they were actually going and building thousands of phones and putting thousands of different fingers onto these thousands of different phones in order to get that training set. It's not the way to do it. So we massively reduce their risk, cost, and their time to market. The other cool thing about the cloud is once all the data is up there, we can enhance collaboration. We can enhance collaboration between electrical engineers and mechanical engineers and aerospace engineers. So it's kind of like, think about a Dropbox for engineering data or a GitHub repo for engineering data. Of course, we're a SaaS company, so you can try it out for free. I'm not trying to sell it to you, but go check it out. And we're breaking the legacy licensing model. So the legacy CAE, you had this like one engineer, one license, one computer model. That model is going away. And the new model for cloud CAE is you got a bunch of engineers, you have basically infinite computing hardware on the cloud, no licenses, and you have many, many, many simulations that these engineers can run. And then we charge a unified pricing model. The reason we're able to do this is because our multiphysics solvers are super efficient. A lot of the legacy vendors that sell engineering software today, they bought a bunch of solvers and smashed them together under the hood, and they're very inefficient. Our solvers are very efficient, and they scale out. So they scale across thousands of different instances and hundreds of thousands of different cores on Cloud HPC infrastructure. And they are fully coupled. So when our legacy competitors, they're trying to do a mechanical, electrical, and EM analysis, for example, for like an RF front end, those are all separate solvers. So mechanical solver does its thing first, then it spits data into an electrical solver that spits data into a EM solver. What we do is we actually do all of that together, fully coupled multiphysics on the same finite element matrix or same mesh. And because we do fully coupled physics, we're able to split up the model over tens of thousands of cores. Very soon this will be hundreds of thousands or millions of cores on Cloud HPC, and we're able to do these massive multi-billion degree of freedom models that are impossible any other way. And if our competitors try to do that same thing, they're not as efficient. So they kind of get a point of diminishing returns as the number of CPU cores increases. they don't get the same acceleration or time multiple that we get. So why are we doing this now? The reason that the time is right is because these new technologies that you guys created are ripe for innovation. We had Kubernetes clusters come out in 2015. We had Docker containers come out in 2016. We had true bare metal HPCs. We've got NVIDIA that's going to give us millions of cores of GPUs on the cloud. That's awesome. We got new licensing methods, new business models, new ways of paying for this. And these guys have been waiting for this type of application. We're not doing HPC just for HPC's sake or AI just for AI's sake. What OnScale is it's an app that engineers can use, and it helps make getting engineers access to HPC and AI simpler. And then we're building up our fully coupled physics. We're doing parallelism on day one, and we're going to move that 100 billion core hours of engineering compute loads into the cloud, and hopefully scale up that number until it's trillions of core hours per year. So summary is CAE is a massive HPC and AI workload. 99% of it is on-premise today. That's the big opportunity. And 99% of it is sold under like legacy business models. I think that in 3 to 5 years, you'll see the vast majority of this move over to cloud computing because it makes the most sense. So there's my contact info. Feel free to reach out if you've got any questions. And I'll take a couple of questions right now. Yes, sir.
So in engineering and scientific simulation, sometimes you have this chaos, which was mentioned, or bifurcation, where a slight change in the input condition can cause drastic different outcome. Is that something that's learnable?
It is learnable. And what we call that AI-guided engineering. So the old adage is like that George Box quote, all models are wrong, some are useful, and also garbage in, garbage out. So the biggest challenges that younger engineers have is like, how do I set up my model so that I get accurate results? And if I tweak something, will it like run off into space and give me inaccurate results? So we're actually using AI to help engineers set up their models and boundary conditions and everything so they don't make those kinds of mistakes. Yes, sir.
When you talked about the billion-dollar plane, there is a physical aspect where you're actually fabricating the device.
Yeah.
So how do you solve that here?
Well, you're always going to have the prototype. The thing that we're suggesting is spend a lot more time and money on engineering analysis before you prototype, and cut your prototyping efforts down by 90% or more. And we do that in a lot of cases. Like in that ultrasonic fingerprint case, engineers literally made thousands of phones to test sensors. And we're saying, hey guys, you're gonna have to do that anyway. But like before you go do that and commit to a design, do 1,000 or 1,000,000 or 1,000,000,000 virtual simulations of that device so you can find stuff. You can catch design flaws earlier in the process. Does that make sense? All right, cool. Yes, sir.
What type of hardware does your software currently run on in terms of number of GPUs per CPU?
So we currently run on CPUs only. We are refactoring to run some things like fluid dynamics on GPUs. This is all highly linear sets of partial differential equations, so it works really well on GPUs. In the future, we will have sort of a mix of CPUs, GPUs, maybe even some more advanced stuff that I can't really talk about now, but advanced computing architectures that are set up for engineering analysis. And the takeaway is, if you're an engineer, you don't care if your simulation is running on a CPU or a GPU or an FPGA or whatever. All you care about is like getting the data as fast as you can get it. So it's our job at OnScale to figure out what type of computing architecture to run pieces of your simulation on. Great question. Yeah, in the back there.
So what about data residency? Are your customers using it all in the cloud? What about their security concerns?
Yeah, we get that question from every one of our customers. Security, yeah, security is super important. This, for a lot of these companies in highly competitive markets, these are the crown jewels, this is intellectual property. And what we like to say is, it's your cloud. We're just giving you better access to it. And what that means is we've built everything on AWS and Google and very soon Alibaba components. So if people are trying to hack OnScale, they're actually trying to hack AWS, which has like the best security in the world. In fact, it's better than any on-premise data center. Does that answer your question? Yes, sir.
So is this like available in the marketplace?
Yeah.
So it's just an application you apply, and then you guys would designate, you would, based on the workload, designate a certain amount of time.
Yep.
Per hour.
Yeah, so if you're an engineer, you can go right now, download OnScale. It's a thin client that runs on your PC. You set up the model on your PC, and then when you're about to hit run, it'll calculate how many core hours in RAM and how long it will take to do that simulation or set of simulations. And then it will say, are you sure you want to go below 10,000 core hours on this simulation study? And you can say yes. And then we create the hardware infrastructure, solve the problem, store the data.
So you can set up parameters and blocks so that.
Yeah. Yeah, behind this, there's a management portal where like an engineering manager. Yeah, you can't like, that's like the second, that's the first question is security. Second question is like, okay, if I give my engineers 1 billion core hours, how can I tell if they're like using it effectively? And we have a management portal where if you're an engineering manager, you have an account with OnScale, you get 100,000 core hours, and you can give 10,000 core hours to this engineer, 10,000 to that engineer, and you can monitor how much they're spending, which is also kind of cool in itself because you can see the effectiveness of your engineering team.
So it has dashboards.
Yeah, it's got dashboards and analytics and all that stuff.